everyone, I'm gonna talk about uniform linear array signal model, and then I will compute correlation metrics for this signal. This is the first step to array signal processing field or spatial signal processing. We can divide signal processing into main branches: temporal signal processing and spatial signal processing or array signal processing. In array signal processing, you have some sensors, for example, some antennas or some microphones, and based on these sensors, you try to sense the space and you can do a spatial processing. Let's start talking about uniform linear array model. You see this figure, this is the figure of uniform linear array. What is linear array? It means all sensors are in a line. And what is uniform? Because the space between sensors are equal and it is D. So uniform linear array is an array formed by some sensors. They are in a line with the same space. Before I start finding the signal model for this array, I should divide signal into main categories: narrowband and wideband. Two categories for signals, narrowband and wideband. It refers to the relative bandwidth, actually. Bandwidth over center frequency of signal is lower than 1 or it's small. We can consider our signal is narrowband, and in this modeling I assume our signal is narrowband. In narrowband signal we are able to model signal with sinusoidal signals, and I assume the complex form or baseband form of signals. The second point that I would like to remind you, in a complex sinusoidal, for example, when we have st ej omega ct, time delay appears as phase shift. This is the key here. st minus tau equals to e minus j omega c tau e j omega ct. We have here minus omega c tau as a phase shift. So time delay appears as phase shift. Actually, time delay converted to phase shift in narrowband signal processing. Okay, let's start. In this scenario, we start talking and studying about this scenario. We have a source, and actually we have many sources, but I started with one source. Then I can extend it to n sources. So we have some sources, some signals. From that sources we receive a wave. And the next assumption that I make here is source is in far field. When I assume far field, then waves appear in plane. Actually, they are not spherical, it's plane because of this assumption. We assume source is in far field, so we have some plane parallel to each other comes to the array. And this is the second point. Okay. Another point is I assume a reference point. For example, I consider the first sensor of this array is reference point, and I assume that the signal ST received from the source to the first sensor. Now, what about the second sensor? First plane comes to the first sensor, as you see, then comes to the next, and then come to the next, and moving forward. So in an ideal condition, or in a calibrated scenarios, when channel is ideal, actually we have a time delay. When wave comes from here to here, we have this length, so we have delay. So the signal that received to the second sensor equals to ST minus tau. What is tau? What is the distance? D sinus theta, where theta is the DOA, or direction of arrival of source. D sinus theta over C. C is the speed of wave. Here, for example, we consider electromagnetic waves, so C equals to, and this delay, because our signal is complex, converted to phase shift. So I can write E minus J omega C D sinus theta over C multiplied by ST. What about other sensors? Also, they are also have delay with respect to ST. I can write tau k equals to k minus 1 d sinus theta over C. So, based on this fact, I can write the signal that received to the all M sensors. The received signal vector y equals to the first signal that received to the first sensor is ST, and I put 1 here, reference sensor, reference point, the first sensor. But the second one has a phase shift with respect to the reference point. We have E minus J omega C d sinus theta over C. The second is minus J 2 omega C d sinus theta over C. And the last one is E minus J omega minus M minus 1 omega C d sinus theta over C. And we also have noise for each sensor. E1, noise of the first sensor, E2, and EM2. Let's talk about this vector. We call it array vector or steering vector. We call it array vector, which is highly important in array processing. We can simplify omega C d sinus theta over C equals to 2 pi d sinus theta over C over Fc carrier frequency. C over Fc is the wavelength of the wave. So we have 2 pi d sinus theta over lambda. Actually, we call this a spatial frequency. We had temporal frequency before in time processing. Now we have a spatial frequency. 2 pi, d sinus theta over c. So based on this, array vector equals to 1 e minus j 2 pi fs e minus j 2 pi 2 fs Van der Monde vector. This is Van der Monde vector. Okay, first of all, based on the symmetry of with the array line, theta has to be between theta must be between minus 90 degree and 90 degree. Because for example, theta 0, wave comes from the front and theta equals to p waves from here, and these 2 points are symmetric to the array line. What does it mean? It means delay in these 2 scenarios are equal. So to prevent ambiguity, we have to consider, we have to have this limitation in uniform array. Theta belongs to minus 90 degree and 90 degree. This is the first point that you should consider about array model. And what about the second point about array vector? As you see, it seems you have a signal. This is actually the simple of a complex sine. This is the sample of a complex sinusoid. For example, you have e minus j omega x, for example, f x. Then you sample this function and you use f, for example, n d. D is a period of sampling equals to e minus j omega d n. And as you see now, omega d is a digital frequency of the signal and must be lower than pi. You know that from the discrete time signal frequency is limited to the pi. So I have to write 2 pi d sinus theta over lambda lower than pi, and we can consider d lower than lambda over 2 absolute value sinus theta. And if I want to satisfy this condition for all theta, I should consider the actually lower bound, a small bound, which is d lower than lambda over 2. This is another condition that you should consider in uniform linear array. The space between your sensors must be lower than lambda over 2. There is an analogy between this condition and the Nyquist condition. Because of that, we call this a spatial sampling theorem. A spatial sampling theorem. Where this come from? From the sampling. Actually, we have a spatial sampling. When you have different sensors, that means you want to sample the space. And the space between the sensors are your period of sampling. What we have until now? For a source with DOA theta, the received signal equals to A theta array vector signal plus noise vector. And consider the scenario that we have multiple signal, n sources with different DOA. In this scenario, what should we have? It's simply the superposition is hold here, so I can simply write yt equals to a theta 1 s1 plus a theta 2 s2 plus a theta n sn plus noise vector. And I can arrange this by a theta 1 is the first column of this matrix, a theta 2 is the second column, and a theta n is the last column. Multiply by S1, S2 signal vector, Sn, n is number of sources or number of signal. Interesting thing, what is this matrix? This is a Vandermonde matrix and name it A. This is a Vandermonde matrix, M by N. M number of sensors, N number of targets of number of sources, and this is the signal vector. So finally we have the signal vector equals to A S T plus E T. This is the array signal model when we consider the uniform linear array. The last point, we want to find the covariance matrix for this signal. I assume noise is spatially correlated with equal variance and signals are orthogonal. It means expected value SIT SJT conjugate equals to 0. So correlation matrix R equals to YT Y Hermitian T. Because signal and noise are independent, there are two terms only remain after taking expectation, which are A expected value ST S Hermitian T A Hermitian plus sigma 2 IM. Expected value SS Hermitian is a diagonal matrix. I call it P, which forms by the power of each sources. The first source, for example, alpha 1 square. The second source, alpha 2 squared, and the last one alpha n squared, and others are 0 because I assume signals are orthogonal or non-coherent. In the case of coherent or correlated signal, this will be different. Okay, finally we have R equals to AP, A Hermitian, plus sigma squared I. This is the correlation matrix for the array signal model. When you have R, actually you don't have real R. You can estimate it based on the n snapshots. Based on this estimate, then you can use music algorithm for DO estimation, ESPRIT algorithm for DO estimation, Kaplan algorithm for DO estimation, mean norm algorithm for DO estimation, NLS or deterministic ML for DO estimation, stochastic maximum likelihood for DOA estimation, and periodogram, and many more. And you can see in my channel I talked about before about music algorithm, ESPRIT algorithm, Kaplan algorithm, minimum norm algorithm, and based on those algorithms you can estimate DOA. You can do actually DOA estimation. Thank you for watching this video. I hope you enjoy it. Please subscribe my channel to see more videos regarding signal processing and array processing and machine learning.